Welcome back to the Rollup High Roller community. As always, nothing on the Rollup is to be construed as financial advice. We are just some educators in the DeFi space. Toss us a quick like, give us a share, a repost, send it to a friend who may want to watch this, and finally, give us a sub or a follow. It means the world to help support credibly neutral educational content in DeFi. We're here to educate, empower, and enrich you, and let's jump in.
Let's talk some more Booster Rollups again.
Yes, welcome, Brecht. Welcome to the Rollup. Yep.
I guess.
Tell me, where did you find this picture, Brecht?
Oh, so like when I made like my Twitter thread, like 2 months ago or something, I created like a couple of like these logos using AI, and I think AI should generate some good ones. But yeah. On Twitter, I used like the most dumb one, and this is still like a pretty dumb one, but it's also like a nice and dumb one. So I just use this for the presentation. I still have a couple of more. Like you can expect more of these logos to pop up in the future. Hopefully,
more memes from the Taiko team.
Yeah,
big memes.
I have a backlog, so be prepared. Okay. But let's
congrats on the. Yes, congrats on the testnet for Taiko. Looks great. I know a lot of people were excited about that. And yeah, man.
Yeah, thanks. At least like two days of uptime now. Hopefully it stays working as expected. And yeah, hopefully also we don't find any like big troubles or something. So this is kind of like the final release, except for like some small modifications for like the main method. But yeah, exciting time. But also exciting. Booster Rollups, which is what we'll be working on the next couple of months. Well, I guess like we'll have to see like how long it will take. But let's say this is kind of like expected maybe 1 yearish year out or something before we get like everything up and running to kind of like switch the design. I'm also like optimistic a lot of the time, so we'll have to see like when it will actually drop it. I think that's kind of like a good time frame for us to work against. But yeah, so Booster Rollups, what's the problem that we're trying to solve? Like, what's kind of like the design? Like, how do we solve it? What's kind of like the pros and the cons? I'm gonna give some more details of like how we will actually try to do this. Like, why we think this kind of like good solution, and like what problems does it solve? What problems it doesn't solve? So the Ethereum roadmap is kind of like, okay, we have like the L1 on Ethereum, like Ethereum is L1, and then we have like the rollups that kind of like plug into the Ethereum, and then we can actually scale, and it's kind of like a good system because without having like some kind of like, well, let's use the fancy word, enshrined anything. There's actually like different like rollups that can experiment and kind of like try different things out, try to like scale things in like the best way possible. So it's kind of like a very nice roadmap where like people, basically L2 teams, can do whatever they want, and they can like experiment with stuff and then see like how it goes, and then we'll see like what ends up winning. But instead of like Ethereum team itself like saying like this is kind of like the way to do L2s, it's kind of like a very open design space. So that's cool to see. But yeah, what's kind of like the well, not a downside, but like one result is that there are like multiple L2s now. And each L2 also has like a limited like throughput or like capacity to actually process transactions and that kind of like stuff. So then you have like the L1, then multiple L2s, and then each L2 has like some applications available. Maybe you have like your smart wallet on like one L2, but there's like an application that you want to use on the other L2. And then you have to do like slow bridging, or your bridging depends on like liquidity bridges. to get there, which like it will be more costly than just being able to natively bridge. And there's also like like there will be some delays in most cases. So that's kind of like how do we solve this like fragmentation problem? Although it's kind of like fragmentation, a loaded term, but it is kind of like fragmented in like different silos that kind of like all work like on their own without directly working together. So and the other thing is also like with like the L2s, they have like their own like sequences pipeline. So that's also like what Taiko tries to do, like with like a based rollup. So we use the L1 validators to basically like sequence the blocks, or at least like decide what blocks get into the Ethereum chain. And so that's where also like a lot of like benefit is, because if you want to do like transactions on multiple rollups, then being able to go through like the base system, there is actually somebody that can build blocks for both L2s at the same time. So they can actually include your transaction for both L2s. So that's kind of like the setup. So we have to scale Ethereum as good as possible. L2s also have like scalability bottlenecks. So how do we kind of like work around that to still have like something that users can interact with as if it's kind of like a single chain, or at least that's kind of like the goal. Because from like a user perspective, that would be like the ideal case. So how does bridging normally work? And also like on our current Taiko is basically you write something on one L2, and then on the other L2 you wait on like the other the source L2 to kind of like finalize and also like be fully verified. And then when the other L2 knows the block hash of your source rollup, then you can use like the block hash contains like the state root, and you can actually go through that block hash to be able to see like, okay, this thing actually happened on the source chain. So for example, I proved that I burned like 1 ETH on there. Then on the destination chain, I could say like, okay, this guy like burned like 1 ETH on there. Now mint me 1 ETH on this rollup that I'm currently on. So that's kind of like a good system for like asynchronous bridging, because you can do like fully trustless, because as long as the block hash is verified and you can show like this Merkle proof that this thing happened on the source chain, then this is like a fully trustless process. So it's cool, but the downside is that like you have to wait on the zero knowledge proof or some other proving system to kind of like finalize your like the source L2 block hash, and then you still have to put like this Merkle proof on chain for like something that happened in the past, and this is kind of like also like quite expensive. So that's kind of like how most like trustless bridges currently work without using like liquidity providers. So that's kind of like the current state of like, okay, what kind of like happens when you have like a single L2, then you have like on the L1, you have like a single smart contract there. You kind of like also use it as like a bridge in some way. And then the L2 kind of like has like a similar like setup where there's like also like a bridge contract. And so if you want to bridge in this case, it kind of like works because you bridge from L1 to L2. There's only like L1, L2, so that's fine. You do whatever you want. And then if you want to get out, you kind of like bridge back to the L1. So this setup makes a lot of sense if there's only like one L2. Now, problem is if you have like multiple L2s to scale even more, then if you kind of like do the naive way, then all these different rollups have their own bridges. And then all the L2, you also have like these bridges that depend on like their L1 specific bridge. So if you want to go, like, you're on like one L2 and you want to do something on another L2, you have to go through the L1 basically, because you're like, for example, if you want to transfer 1 ETH from one L2 to the other, then the bridge contract on L1 will store that 1 ETH. So if your 1 ETH is now for another rollup, that 1 ETH somehow has to move from this in a smart contract on L1 to the other smart contract on L1. So that kind of like is a transfer on L1, which will be expensive and also like a slow progress because you have to go through like all this like verification mechanism that I talked about before. So this is like a very inconvenient way to actually scale with L2s if you have like multiple L2s. So you can improve on that. So for example, if instead of like different L1 smart contracts with like different L1 bridges or that kind of like store all the funds, you just have like a one, and then all L2s kind of like hook up into like this single bridge. So that's also like much more convenient already, because now if you do transfer like 1 ETH from one L2 to the other, you don't actually have to do any transfers on L1 because all the L2s use this like shared bridge, and that one ETH will be at the correct bridge even if you go from one L2 to the other. So that's kind of like a good system. But if you still depend on like storage proofs directly, it's still like asynchronous. So you do have to write something on one L2, wait on things to finalize, and then on the other L2 you kind of like have to prove it. So it's still like it can take a while before you can actually bridge those. And then like then the improvement on top of that is like instead of like asynchronous, so you have to wait, you can actually do like synchronous bridging from one L2 to the other. And so one thing that was previously like proposed there was like shared validity rules. Sorry, I forgot like the company that proposed it, but yeah, it's a new Umbra Research, I think, but I could be wrong. So they proposed like using like a smart contract on like the L2s to say like, okay, instead of like writing something to so like some smart contract on one L2 and then reading it on the other L2, it's kind of like part of like your validity rules of all the L2s. So you would say like, okay, there's like this bus contract, and on both L2s you kind of like have to do like, okay, there's one ETH that needs to be transferred. Both need to kind of like write something to it, and then you can say like, okay, for this L2 to be valid, both L2s need to have written this data to like this special contract, and that way you can actually solve like any asynchronous problems, and you can make it like fully synchronous. But it does have like problems because now, for example, each L2 doesn't have like its own validity rules, because writing something to a smart contract L2 can be valid for the L2 itself. But now we also depend on like this opposite L2 where you did the bridging from or to also have done that right. And otherwise, if that didn't happen, then you didn't follow the rules of like this the synchronous bridging. So that means that, yeah, this L2 block is valid for the L2 itself, but it's not valid in kind of like this whole system of L2s. So this block would still need to be like reverted or ejected, even though the transaction was actually executed correctly. So that's kind of like the downside of this. And yeah, that's why I say here that if you actually want to do this system in like a way that doesn't depend on like some optimistic again mechanisms, or having like everybody required to run nodes for all the L2s, you would have to depend on, okay, I run like a node for one specific L2, but I can actually depend on very cheap to verify proofs for all the other L2s. So I don't have to run nodes for those. I just have to check the proofs for those. And then for my own nodes, okay, I can actually check everything is correct myself. So this kind of like depends on like fast proofs basically. So if you like propose a transaction, a proposal like these blocks that kind of like are interconnected, then you kind of like enforce this kind of like requirement of, okay, if I want to keep things fast and like mostly like trustless, then fully trustless if you have like lots of proofs there, then you can actually make this like very well. But yeah, this does depend on like fast proofs, and ZK proofs are pretty fast already, but we're not as fast as necessary to actually make this as like block proposer time, because like ideally you can actually create these proofs in like one block time or something
Right.
like that, especially for like based rollups.
Yeah, that's the only current major trade-off that we've seen consistently with the ZK side. Two things on this side. First, is there a difference in L2 shared sequencing where there's this notion of atomic inclusion of transactions as well as atomic execution? Are these one and the same when it comes to shared sequencing with rollups? So basically, you take all these transactions, shared, you sequence them across multiple different rollups. They're all put in the same block. Is that atomic inclusion and execution, or there's some sort of like minuscule time difference which causes it to be like almost atomically composable rather than like fully atomically composable?
Yeah, for normally shared sequencers, just do the ordering, so they can enforce that your transaction is included on all the L2s that you want to do it, but it doesn't enforce that if like your transaction, your like all these transactions need to like succeed. Because if your transaction fails on like your source rollup to actually like burn something and you want to mint it on the other side, then if your burn fails, then your mint will also fail. So it's kind of like it doesn't enforce like both to be at the same time, and that can give some issues. So there are some like workarounds for it. Also like with also like some liquidity providing mechanism to say like, okay, yeah, you can actually get there, but then it's kind of like not capital efficient. So it's kind of like duplicating the funds on both chains. I think that's the latest or like the best possible solutions that's currently put forward to actually do like atomic like execution instead of like just like inclusion guarantees.
Yeah, that's what I was thinking. Because there's difference between ordering and then also executing. And then my other thing on this slide, and I feel like what you guys are building with the Based Boosted Rollups are kind of solving this in a sense where, let's say these L2s here have like centralized sequencers, just like typical current state of rollups. With these bus contracts and with these interoperability, whether it be by shared sequencer or just kind of bridges as is, if one of these L2s were to for some reason have major downtime, how does that affect the state of the other L2s, which are, I guess, horizontally integrated with shared sequencing or with some sort of like bridging mechanism? Like, is there cause for catastrophic kind of issues or in shared sequencers kind of like if one rollup has some serious downtime, they can kind of just almost like isolate that and then once it gets back up, the state is realigned? Or like in the sense of downtime, how does shared sequencing kind of protect users or funds on other rollups which don't go down?
I would say basically none, like no extra guarantees, because like if you have your funds on one L2 and you want to do something on like a specific L2 or you have your money there, then if that rollup is like down or like live, not live for some reason because the sequencer is down, then you cannot work around that because that's the only place you will have your state stored. So in that case, that cannot happen, and that's also like why using like centralized components is like a bad thing, right? So that's also like what like doing like a based rollup solves. So as long as L1 is actually live for a based rollup, and there is somebody that is willing to create a block, anybody at all, then the system keeps going, and you can actually interact with the chain as you expect to do.
Love it. Yeah, I figured that's what you guys were solving for. So, all right, onwards and upwards.
All right. So that's the fast proof things. Ziki is not there yet, but for example, like TEs, like SGX that we currently launched just now on our testnet, they can do like very fast proofing of the blocks, right? So that's kind of like a very convenient way we can actually already have like very strong guarantees of like the initial, like even at when the block is proposed, we can already have like very good guarantees that whatever the proposer posted is actually the correct state, and people can already depend on it to make subsequent blocks. So this is cool system, but what we're trying to also solve with like Booster Rollups is a little bit more than just this. So in this case, we still have like the problem where each L2 is kind of like its isolated state. So if you have like whatever application that you want to use. So you have like all the common ones. So like Uniswap is of course like a very good example because everybody wants to use Uniswap. So you kind of like depend on Uniswap specifically deploying to whatever L2 you actually are interested in using. So that's kind of like a big problem, especially if you expect like a lot of like L2s to have to be created, right? So if you have like 100 L2s that you eventually need to scale, then having to deploy like each application, having to deploy this to this like L2 that you kind of like want to have available everywhere is kind of like a hard thing to get developers to do, and also kind of like maintain, right? Because like these applications mostly are still being updated. So if you have like an update for your application, then you have to do it at like all the different places or all the L2s and have to go through all the hassle to do that. You first you have to get your application there, then you have to keep it updated, and users will go where applications go are at least if like these, especially if there's like no convenient way to like bridge or like if that's kind of like not a great user experience. The other thing is like currently most L2s, although like it's more like a practical thing because in theory you could have like multiple bridges for most tokens, but in practice mostly people just use like you kind of like have to wrap your token contract on L1 to be able to bridge it from like L1 to L2, and so these are kind of like very security critical things, because if there's like a bug in your bridge, then basically all the funds that are stored on L2, you can just get it out. So not having like a single point of failure there for security would also be a great thing to have. So yeah, and currently like a lot of like interesting state is still on L1, right? So not being able to access anything on L1 is like very inconvenient, because for the most common case, of course, you want to deposit something from L1 to L2, so you have to be able to read the L1 for that. So that's kind of like a very common case. But also for things like, you have like your smart wallet on L1, you also want to use that smart wallet on L2 or like multiple L2s. So that would also be like a case where, okay, I kind of like set my like multi-sig up on L1. That's where all the state is stored. And actually, I want to just use that state on all the L2s that also use my smart wallet too. So that's also kind of like a thing that makes it like much more convenient, because compared to like apps that you have to keep updated everywhere, also users have kind of like the states where they have like a smart wallet, they have like multiple gardens, they have to keep it up to date between all the L2s that they kind of like interact with. So that's where Vitalik also wrote like a post about this, using like key stores and like one chain having like a key store, and then you just access that key store on all the chains. So that's also, if you use the L1, that's kind of like currently like the most convenient way to do it, because automatically all L2s have access to the L1 in some way. But even in the future, doing anything on L1 will be expensive. So you will also have to be able to read from L2s in a cool way.
Yep. It's a cold start problem for developers and for builders. It's like, well, you need to deploy across this many optimistic and ZK rollups. Why do you have to redeploy your contracts and your app, across all of these chains? You need to necessarily perhaps write new parameters for different codes. And then also the issue here comes again with updates, right? Like, okay, the first time you deploy an app across 10 chains, okay, fine. It's a headache, but you got it out there. Now you're, multi-chain crushing, whatever you want to call it. But then you got to launch a D2. You have to pay for audits on your code. And then you have to make sure that all the audits for every single chain, with the slight differences, if there are any, between, L1, L2, ZK, optimistic, or alternative L1, or EM compatible sidechain, or there's all these different kind of like intricacies. So, what's the solution? What's the solution? We're getting close.
So that's also like a good point that I didn't mention explicitly, but so I guess it's part of the solution. But being like a type 1 ZK EVM, or being like fully Ethereum equivalent is like very useful here, because then there are no changes that you do between like all the Ethereum equivalent chains. And also for like the last one, I guess it's also like having like a standard or like an automatic way to actually construct like cross-chain transactions is also kind of like an important thing. So ENS actually has like some interesting EIPs about this. But if you, for example, do like a bridge transaction, even like today, then you do like a transaction on L1 for like a deposit, and then you somehow have to know like what to do on the opposite side of the transaction, right? And there's like no standard way to kind of like know like, okay, if I did this thing on L1, what do I actually have to do on the other L2 to get my money there? So that kind of like a standard way to interact with like multiple L2s is also like an important thing. Okay, so what does the Booster Rollup do? What is the basic idea here for like the Booster Rollup is that instead of like having to deploy instead of having like an L2 start from scratch, or like having no state, having no smart contracts, having nothing at all, each L2 would basically like have like a built-in mirror to like the L1 or whatever parent chain there is there. So you would be able to say like, okay, I want to interact with like this smart contract L1, but I want to actually do it on L2. You could do this on any like Booster Rollup that will be deployed from the start. So it's not like a wasteland there. You can actually just add like an extra rollup to the system, and you can already start doing whatever you want there. So if, for example, kind of like the ideal case, and also like a very simple example is kind of like just token contracts. So if you have like a chain where you have to do like lots of like stable coin transfers, then the only thing you have to do is basically add this Booster Rollup, and you already automatically have like the token smart contract for USDC or USDT available there, and you can already do like transfers on that rollup there. So you will automatically add like extra capacity to the system. Although, like to be clear, there will still be like specific L2 state, right? So it's not automatically like, okay, yeah, you have like all the state there. You would still have to query the state from the correct rollup, basically. But yeah,
the
not like
the L2s it's still distinguished between the other L2s as well as L1.
Yeah, exactly.
Right, which is very important for like for security as well as like verifiability.
Yeah, scalability. So yeah, if you so for example, like the thing that's most important for like a rollup is that you can actually like you have some money stored on your L2, and normally you can depend on like proposers, builders, whatever to actually you give them your transaction, they will handle it for you, and you get your money out. So for rollups, the important thing here is that you do not have to depend on others to actually do that to be able to get your money out. So it still needs to be easy enough to run like an L2 node on your own, so that you can actually build a block, like process your own withdrawal transaction yourself, and so exit the system. So that's why for each L2 specifically, the requirements and like the storage required for it still needs to be kept in like somehow limited, and so like so it's a limited capacity per L2, but by having like lots of them, you kind of like increase the scalability.
Yeah. So real quick on this, which brings up like, of course, the point of the top of the hour for us and top of mind is the modular blockchain stuff, right? Separating these rollups. So with boosted rollups, as far as data storage goes, how does that work? And is that something that you guys are looking into? Does it all just post to the L1? Is that kind of like how it works? Or can you use like Celestia or Reveal or insert DA layers here? Or kind of like, what's your thought there?
Yeah, in theory, the data availability layer is like, you could pick whatever one you like, because we do not depend on like any specific ones for the rollup to work. So as long as the data is accessible to nodes in some way, it should work. But obviously, like data availability sampling solutions are like very interesting. So like Celestia is kind of like the obvious case, but also like the restaking one from EigenLayer would also be very interesting. But yeah, it's kind of like we're at like an interesting point in time where like in 2 months we will actually have like lots of like more data availability capacity just on Ethereum itself, because of like EIP 4844 shipping. And so
the data availability wars are happening. Like you got these pairs launching mainnet this quarter, and then also EIP 4844. Ethereum's going from computational roadmap to like data focused roadmap. So it's just going to be like a freaking battle. I think it's going to be interesting. Either way, the thing that I love about this and about what you guys are building is that users get cheaper costs, more security, and better experience, no matter who kind of wins, right? Some trade-offs, there's some kind of intricacies, but overall, the users are the ones who end up winning from these like innovation battles, if you will.
Yeah. So we'll have to see like how ideally, of course, we stick with Ethereum because if you add assumptions to like another chain, then it does worsen your security. So that's why I think it's like smart to see like how things will actually progress on Ethereum, because in 2 months or 3 months, this will actually be available on Ethereum in like a limited capacity at least. But like nobody can really know like what the data availability costs will be, because this has like the data availability costs in EIP 4844 has its own fee market, and this fee market is kind of like similar to like the normal transaction fee market, where like the cost is just based on congestion. So if nobody uses the data blocks, then the data blocks are free. So you can't do better than free. So it depends on like how this kind of like is adopted, and like how many L2s will actually start using it, and like how quickly to actually know like, okay, what's is actually the cost of publishing data on Ethereum with EIP 4844, because nobody knows. It's hard to predict. There's like no data. Some people predict like 10x improvement, but it's just like, it's kind of like mostly guesswork, because it all depends on like who uses it and how much it's used. So it doesn't, it doesn't make sense to use something like Celestia. Well, maybe they're cheaper, maybe not cheaper. Like how long will it be cheaper? Who knows?
And the security, it's a trade-off, right? And I also think it's use case specific. Something more financially secure, tons of TVL, perhaps posting to Ethereum using EIP for its cost benefits makes sense. Something less financially, important, perhaps using alternative DA for just UX speed and even lower costs. But again, it's yet to be seen. So we're still in the early innings of this, which is exciting. And I think that idea of not needing to charge the rollup, the sequencer not needing to process blocks, there's no transactions, is very helpful for early stage app chains or early stage rollups who may not have that much traction, where they don't have to pay for the blocks every single couple of seconds if no one's using it. It allows them to look at the revenue models for how they're going to make money, or at least how they're going to reach sustainability. And the fixed costs of having to pay for each block kind of goes down to more variable cost based on usage. So it's interesting. Onwards and upwards. So boosted rollups.
Yep. All right. Yeah, this slide is just from the article, but I think it's a good one. So to make it clear, like what's the idea is like, yeah, well, you have like a limited kind of like L2s, but if you need more, then sure, like plug one in, and you kind of like have like the initial state there that you can start using. So I think this is kind of like a good way to visualize that for people. So it's kind of like, plugging in a booster rollup is like, adding like the CPU and like extra storage to your chain, which might be easy for people to understand. I don't know, but seems something reasonable for people to understand. So this kind of like, so the idea is here also that like the amount of like booster rollups coming in the system, like would be able to get like very high, right? So there would be no problem with spending like, 1,000 of these kind of like working in the system. So that's the goal.
And when you add more, does it increase? Is there any benefit for the existing ones? Are they using shared sequencing across them, or is there some sort of I understand that sequencing is happening at the L1 layer, but is there costs that are socialized, or is there any benefits to having 10,000, a million, or does it just kind of scale as it is and there's no downside to having more?
There should be like no downside in adding more for users. It's just that so there's a couple of things, like why would you add more, right? So that means that you would add more if somehow the other kind of like are congested. And so if they are congested, so we use like EIP 15F9 on RL2. So if things are kind of congested, then the base P will go up. So user transactions will be more expensive, right? On this specific booster wallet. So if you say like, wait, this is kind of like, for example, my smart wallet is on like this booster rollup with like very high fees, then you might like want to look into like actually migrating to another one with like cheaper fees. So that's kind of like, if you add like a new one, then there won't be like lots of activity there, and you can just like move there and then still very easily interact with whatever other rollup you want for like specific like liquidity pools that are still like the most liquid on like a specific, or somehow not like fully opt into the system, right? Because for like smart contracts to fully take advantage of the system, they would still have to like be able to like do these like cross-chain transactions inside the system. So for example, like if you have like smart wallet and you want to do something on like another chain, then your smart wallet does have to say like, okay, I want to interact with like the specific other there. Although there's some ways you could try to like solve that, but at least that's not part of the current scope. So this is kind of like how it would work.
Love it.
Yep. So yeah, I guess like this is kind of like the example for like the smart wallet case, together with like some interesting like L1 uses as well. So if you have like your smart wallet on like one L2, and you want to interact with like some kind of like specific pool that for some reason has most liquidity on like one of the L2s, then you would just do like, okay, start your normal transaction on a specific L2. You do like a call to like another L2 to do a swap. This swap on its own will also do like token transfers on like the different chains. So you could like have your money stored on like whatever L2, and you would just specify what one that is. It will do the transfer there to like the liquidity pool, and then you kind of like bought it by selling your tokens, and then you get your tokens back. So for users, it looks like a normal transaction. So they don't have to do anything. They just have to sign this one smart wallet transaction. And then like the system will just take care of it. So yeah, what I also added here is like the key store. So if the user also has its smart wallet deployed on L1, which isn't required, you can just deploy your smart wallet on a specific L2. But if it's on L1, then you can use like this key store system. So if you execute your smart wallet on L2, then we will actually read what signatures are required to be able to execute a transaction in your smart wallet. And okay, you can just query it directly from the L1. So there's like no delays, no extra proofs necessary, no Merkle proofs that you have to generate, nothing at all. It's just part of like normal smart contract code. You just have to execute this transaction, and it will do everything for you. No manual setup phases.
And so when users are interacting with this, what they don't see under the hood is that when they submit a transaction on the L2, it's actually going to end up being sequenced by the L1 in an Ethereum block. So I'm curious on to how you can take L1 sequencing and get the same low fees and high throughput of L2s, but while taking those transactions and putting them to L1. Like, is there the mechanism in which one transaction on L2 is very cheap, but is also sequenced by L1? How does that work?
Right. So how to best explain it? So things on L1 are priced in gas, right? So you pay gas to do something on L1, and so if you actually execute things, like if you have like a full transaction on L1, then there's a couple of things that you pay for. So first of all, you have like a transaction which needs like its signature validated, and so the base cost is already like 21,000 gas, and then other costs kind of like add up to it. So you have like your transaction needs some data, and the data also requires some to spend some gas, and then obviously like all this smart contract code needs to be executed on L1. So all the smart contract code that needs to be executed also costs gas for your transaction. So all that kind of like they get wrapped up. It's kind of like the total cost for a transaction, and the more people that want to do a transaction on L1, the higher the fee is that you have to pay because the L1 would be congestion. So like how does an L2 actually make things cheaper? Is that there is actually like specific block billers. Like let's keep it not too many details. So there will be like you create like an L2 transaction, and there will be like block billers that kind of like batch all these L2 transactions together. And this batching will then be wrapped up in like another L1 transaction. But the only thing that needs to be done there on L1 is kind of like just saying like, okay, yeah, these are the L2 transactions that need to be done. And it's just the transaction data that you have to post there. Well, there's also like other ways to do it, but in our case as well, it's just like the L2 transaction data that needs to be posted there. So you skip all the like signature checks and kind of like things like that. And also obviously and none of the smart contracts are executed. None of the transactions are actually executed on the L1 that are done on L2. So that's where like the savings come from. So you, instead of like having to execute the transactions actually on L1, which costs gas, now on L2, if you want to put data on Ethereum, the only cost you pay is like this data. And obviously, like if you somehow still have to verify that whatever you did on L2 is correct, so that's where also like the proving comes in, which also comes.
Yeah. And the state is different, right? That makes total sense. So basically, what I'm learning from all these different iterations is like, this is a way to avoid the typical trade-off of like roll up with centralized sequencer, security issues, MEV problems. But with Based Rollups, we're getting to this point where you're getting all the benefits of an L2 and also still really inheriting like the core principles of Ethereum and core properties which make it decentralized and the best kind of settlement.
Yeah. So there's like these batchers of blocks, like L2 transactions that I talked about, like these L2 block billers. So that could be like anyone. So anybody would be able to do that. And then they just have to make like just a normal L1 transaction out of it. And then they just have to be able to push that one L1 transactions through the normal setup. So That's compared to centralized sequencers. So that's like where like users actually submit their L2 transactions directly to like this centralized sequencer, and then only this centralized sequencer can actually push a block of like this aggregated like transactions block on the L1. So they are like the only like block builders in kind of like or the terms that we use. If you use like Based Rollup, that anybody can be a block builder, and you just have to be able to get your block on chain in whatever way you can and would.
Well, onwards and upwards, ladies and gentlemen.
I think we're almost done. Let's see. Okay, yeah. So I think like this is just like some like how does it look like? And this is kind of like the current design, which yeah, it's pretty dark, I guess. Well, I guess like most people don't care anyways. But if you like sit like, okay, how does it actually look like now? And I'm sure like things will still like change as we go along. But yeah, so basically your Solidity code looks exactly the same. There's just like an extra like EVM.call options that you set, and then you can just specify like, okay, I want to do this like this call in like my code, and I want to do this on like another chain. So you can just specify there, and everything else will be done automatically. That's the only thing. And this is the same thing, so we'll skip over it.
So, but the key thing of those 2 points, because yeah, I mean, I those go over my head, but you know, is what it is. Those 2 key points. So it's that the token contract is the same as an L1 token contract, right?
Yeah.
That's the key thing here. And so it's completely replicable from the L1, which allows these things to happen. Which is, again, it solves the problem that we were speaking about earlier with regards to the multiple audits, multiple deployments, different all these different token contracts, right? Even for like having your token on different chains can get confusing for users. Obviously, there's like layer 0 and different types of standards, but at the end of the day, like having with little trust assumptions, the same token contract goes a long way.
Yeah, exactly. So this, for example, like if you have like a token contract, you would actually deploy it on L1 because you want it to be available on all the L2s for forever. And like, the only thing that you would have to do to be able to use this smart contract is deploy just like a Booster Rollup, and then you can just directly use it to interact with things. So the same contract code will execute on L1, L2, wherever on all the Booster Rollups, currently deployed Booster Rollups, future Rollups, anyways, all of them. So you can also like check, like I guess this could be like interesting. So you can also like choose like where you store the state. Like, so for example, you have like a total balance, and this total balance is kind of like shared for all the L2s. So you would actually store this on L1. So you have like this function here that says like, okay, if somebody calls like total balance, then you just want to redirect them to the L1 state. But like for transfers, then you have to be like flexible and say like, okay, I want to go from like this specific to the L1. So I think this is the last slide, but this kind of like, okay, so we have like all these transactions, all these blocks, all these L2s, like how do we actually like, propose a block in this system? And so currently the idea is to have like just like a single transaction list, not all like how shared sequencers also kind of like handle this. So there will be like one large string of like transactions, and block builders would actually block builders would pop up and actually do all these like transactions, create this transaction list, and they would actually build this kind of like in sequence. So that also allows us to like synchronous bridging. And so these block builders we have to see like if there's like 1,000 L2s, these block builders will also have to be like specialized and say like, okay, I can do transactions for like a couple of these like Booster Rollups, but maybe not all of them because they can't like sync all of the state necessary to do that. So you will be able to specify like, okay, this is kind of like my transaction. I touch like all these different rollups. Block builder, just make sure that you have the state to do that. Otherwise, you will not be able to create like this cross rollup transaction. This kind of like one block is it's basically like one block. And so block builders build like this one block of all these like different booster rollups, and the prover will also like just have to prove all this. It's similar to like how a block builder builds this. The prover will also have to prove this single block. So that's kind of like how this works. So that means that depending on like how many of these rollups are actually touched in a block, depends on like how computational heavy the block building will be. But that's fine because block building and proving is done by like very heavy machines, so they can handle that load and they can like be very specialized. But the important thing is here that if you run like your own nodes to be able to exit the rollup if necessary, you only have to care about like one chain. So you just have to filter out transactions that you care about for your own node, and then be able to sync your own node and use it whatever way you like to do it. So yeah, I think that's it.
So because it's a single proof, this cost has been mitigated and shared amongst all of the transactions which that builder puts into the block.
Yeah. Single proof. So so you could have like thousands of these rollups working together in like a single block, and it would still be one proof on chain. So that's also like the benefit of the benefit of this, because if you have like for now you have like 10 rollups, and all these 10 rollups have their own proving systems to prove like a block. But block verification, especially like with the ZK, is also still like quite expensive. It's kind of like 300,000 or 400,000 gas. So if you can kind of like batch them up even more off chain and have like a single proof, then yeah, sure, the proving cost gets a little bit higher. But like the cost you save on that one is significant.
And so with the upcoming EIP 4844, will that also significantly reduce the cost of the proof? Or is that strictly just the data cost for posting? So how is that going to affect the proving cost?
The proving cost will not be directly impacted because for most ZK systems, if you kind of like depend on Starks still have like pretty big proofs. But if people that are actually using it mostly wrap them up in like a snark with like they're using like a recursive proof, where again you kind of like go from a Stark to a snark to be able to minimize the data and the verification cost on chain. So yeah, most proofs I think are like a couple of kilobytes at most, so it won't have like a significant. It will be like much smaller actually, but yeah, it will be like around. But I don't want to put any numbers on it, but it will be a small costs in data for proofs. Most of the costs for proofs for snarks is just like the computational cost. Even though there are pre-compiles, in the end it's still like quite expensive to do, like 300,000 gas.
Makes sense. Well, Brecht, thank you so much for coming out and giving us the really intricate understanding of what a base rollup is and why it's for. And really am excited to see these out in the wild. When can we expect the first Based Boosted Rollup on mainnet?
Yeah, on mainnet, no one can make any promises, but I think a roadmap of like 1 year, 2 years at the most, I think that's very reasonable. I think I hope we can get like more the same as we did with like Taiko now, like having like lots of like test nets to be able to quickly test things out, find like problems, iterate on. I think that could be like already like much quicker. But yeah, mainnet release will require some additional work to get everything ready.
Yes, sir. All right. Well, again, thank you, Brecht, for coming on, and excited for to keep trying out the Taiko testnet that just went live, as well as upcoming mainnet and everything else. The rollup world is very exciting. So, thank you.
Yep. Yeah, it was great to hear it. Thank you.